Hi, my name is Nir. I'm a postdoctoral researcher in Weizmann Institute. In the next 15 minutes or so, I will present my recent work entitled Federated Learning with Quantization Constraints. It's a joint work with Mingze Chen and his supervisors Vince Poo and Shuguang Kui, and with my superb mentor, Yonina Eldar. As we all know, we're nowadays in the deep learning age, and deep learning is often carried out on cloud servers. Namely, we have a server which maintains a very large overparameterized neural network, and it is trained using labeled samples acquired at edge devices such as cell phones, tablets. Now, if this network is trained using a sufficiently large number of training of labeled samples, it should be able to carry out inference reliably, like telling whether this image is a cat or a dog. However, data is often private. For example, the Google keyboard needs to be trained using text messages available at cell phones, which may be private, which users may not be willing to share. This is obviously a problem when we look at neural networks trained to operate on medical data, also on data collected from autonomous vehicles. It may be private. So these privacy issues gave rise to the need for what's called federated learning. Federated learning exploits the increased technical capabilities of edge devices nowadays in order to use them not to send their labeled data to the server, but to train their own networks in a distributed manner and then carry out some sort of centralized aggregation at the server side. And its pros are mostly in privacy. However, there are some challenges associated with this approach. Mostly the issue which will be treated here in this talk is what's called the expensive communications, because we now have to often convey very large parametric models over the uplink channel, which at least for wireless communication, it's known to be much more degraded and rate limited compared to its downlink counterpart. There's also the issue of heterogeneity, namely that each user observes data from a different statistical distribution. We will not explicitly treat it here, but this will be part of the assumptions under which we will carry out our analysis. So in this talk, we will treat the expensive communication issue using quantization tools. So I'll start with a few words about conventional federated learning. Then I will present the scheme we propose, which is based on universal vector quantization. We will show its performance guarantees, a theoretical analysis, and some numerical results. So we'll begin with what is federated learning. Federated learning is usually based on what's called the federated averaging algorithm. The federated averaging algorithm means that we have a server that contains a parameterized neural network, and on each iteration, it sends its network parameters to a set of users. Now, the users each have their own access to the network, and the users have their own training samples, and they can train it using tau SGD iterations on their side. And once they do that, they can obtain the difference between the model they received and the model they trained, and they can convey it to the central server over the bit-constrained uplink channel, and the server can now aggregate them. And the common algorithm to do, though, is just some weighted averaging. Those coefficients alpha k here are just the weighted averaging coefficients. However, the uplink communications, the fact that the users have to convey the model updates, which are very high dimensional, is a challenge because the uplink channel is rate limited. So this problem is treated quite thoroughly in the literature, but usually the following approaches are taken. The first is what's called sparsification, which means that we don't send all the samples, we just send a subset. It can be done by just selecting a random subset. It can be done by doing some random rotation and then subsampling. It can be done by just sending the top gradients, the most dominant ones, only sending them to the server. Note that the fact that the server has to know which random entries we have selected implies that there's some source of common randomness that can be shared, and that obviously can be done by sharing a seed from the server to the users. The other approach is using probabilistic scalar quantization. It can be in the form of a uniform quantization, it can be in the form of non-uniform quantization, but it just means that we take each sample, we convert it to a set of bits, and then we send those bits over the uplink channel, assuming that we have compressed it sufficiently such that the distortion induced by quantization will not deteriorate our ability to recover the global model we desire. So in order to understand what is the right approach, we need to understand what would we have done had we no limitations. So the best encoding decoding method for compressing the vector into over a band-limited, rate-limited channel is to use vector quantization. This is quantization theory tells us that if we take a large set of samples and we jointly quantize them, that's the best approach. Now, we also need to ask not just what's the best thing to do, but also what's the right thing to do for federated learning. So we need to understand what are the characteristics of this setup. So as we said, we can assume that there's some shared common randomness between the server and the users can be obtained by sharing a seed. We know that we cannot assume any prior knowledge on the distribution, which is what's usually done in vector quantization, because the data is heterogeneous. It's very difficult to make such assumption. And we also want it to be simple to implement. In the end of the day, we need it to be implemented on edge devices. So these assumptions and requirements motivates us to explore universal vector quantization. And what do we mean by universal vector quantization? Before that, let us just go on vector quantization on a nutshell. So let's say we have a vector and we want to represent it using a set of bits. So quantization theory tells us that the best way to do so is to take a set of bits and to do some partition of the hyperspace into subsets and to assign each subset into a code word. And this means that we're taking a set of samples and we're assigning a set of bits to each set of samples. And we're doing it to maximize some distortion measure. And Claude Shannon showed us way back that the best way to do that, or at least the optimal trade-off between quantization rate, the number of bits we're assigning per sample, and the distortion achievable, is dictated by what's called rate distortion theory, which is achievable when we're taking the vector size to infinity. Namely, we're jointly quantizing a very, very large number of samples jointly. So we would like to have some complex partition of the hyperspace, but this partition has to depend on the distribution. So we will seek what's called lattice quantization. Lattice quantization is a partition of the hyperspace which does not depend on the distribution. It's a constant partition. So it is universal. It is ignorant of the underlying distribution. But specifically, lattice quantization has some very nice properties. And it gives rise to the scheme called D-third lattice quantization, which operates in the following way. Let's say we want to quantize this vector, which is located here. But so what we do, we first add noise to it. And this noise is located somewhere over, uniformly distributed over the basic cell of the lattice. And it dropped us here. This is the vector plus noise. Then we quantize it, namely we map it to the nearest centroid of a decision region. But then we also remove this noise later in decoding, and we get, in this case, for example, the blue point. Now, this has great statistical properties, this quantization, the quantization properties. One, it achieves very low distortion. And the other very nice property about it is that it converts the quantization error into additive noise, which has a very nice statistical properties. It is mutually independent of what we've quantized. And that's important for us because we do not want to assume any distribution on what we're quantizing. So how would such a scheme be integrated into the federated learning setup? So let's look at this setup here. This is the server. These are each users. And the scheme consists of the following step. We call it UVeQFed, Universal Vector Quantization for Federated Learning. So first, we take the model updates vector and we partition them into subvectors, which will be quantized. Then we add the jitter, the noise, and we apply the lattice quantizer, as we showed earlier. Now, what we obtain up the output of the lattice quantizer is a set of centroids, which are the points to which each subvector was assigned. And then we can compress it further into bits using entropy coding and decoding. Now, entropy coding, there are universal schemes for entropy coding, such as the Lempel-Ziv scheme. So this can be done also without requiring knowledge of the underlying distribution. And on the receiver side, on the server side, you subtract the jitter in order to get subtractive jitter lattice quantization, and then you just aggregate the recovered model updates, the noisy, the distorted one, using conventional federated averaging. Now, the fact that the quantization error is translated just into noise whose statistical distribution is fixed and it is mutually independent of what we're quantizing, allows us to get some very nice theoretical results for the scheme. For example, we can actually bound the distance between what the server recovered and what it wanted to recover as if the quantization was unconstrained. And this is actually upper bounded by this term here, where this zeta k here is just a bound on the gradients of the objective measure, and eta is the step size. So what do we understand from this expression, which appears to be not that meaningful? But let us recall that our scheme converted the quantization into additive noise, which is independent of the updates. So if the averaging coefficient, which is what we have here, behave as 1/k, which means that we're just doing averaging, or just at least that we're assigning reasonably equal weight to the model updates we receive from each user, it means that the error decays as 1/the number of users at each iteration. It means that we have more users, we get less error. And this is for a heterogeneous data setup. And so we actually mitigate the distortion induced by quantization in averaging, because we account for the fact that we know that it will be averaged afterwards. So the fact that the distortion is converted into noise allows this noise to be mitigated in federated averaging. Now we can also see that there's this, it also depends on the step size. And the step size in federated learning usually decays. We know this from analysis of federated learning. It usually decays as 1/the iteration. So it means that also we can say that the noise, the distance between what we want to recover and what we actually recover actually becomes smaller as the iterations progress in federated learning, which is also an important property. And this allows us to actually understand the convergence of federated learning with vector quantization, with universal vector quantization. And for example, if our objective measure is this is our objective f, and fk is the objective of each user, then we can actually bound the expected distance between the actual objective we obtain with the weights we recovered and the desired objective. And we can see that if our select a step size which decays as 1/t, which is what's usually done in federated learning, as 1/the iteration number, we actually get that the overall error behaves as 1/t, namely decays as the iterations progress. And that is the same convergence rate observed for federated learning without any quantization. So while this result is not all that surprising, because it was also observed for other quantized schemes, we can show that our scheme achieves better results than previously proposed quantization schemes for federated learning using numerical examples. So for example, here we compare several schemes proposed for federated learning, two that are based on sparsification, random rotation with uniform quantization, and do some random subsampling with 3 bits quantization. And this QSGDs, quantized SGDs, a leading approach which is based on non-subtractive scalar deterred quantizers for federated learning. And the blue curve here is our performance with one-dimensional lattices, and black curve is the distortion induced with two-dimensional lattices. And then we can see we obtain, the distortion is smaller. And as the bits rate, as the number of bits we're allowing to use grows, it actually gets smaller and smaller. And we can see that numerically, at least our ability to recover the weight is improved compared to previously proposed scheme. And that's not so surprising, because we started from a quantization theory perspective. And we know exactly what there's thing to do for such scenarios from quantization theory. But the fact that the quantization performance is well doesn't necessarily indicate on the federated learning performance. But for our case, it does. So for example, this is an MNIST data set, which we trained using 15 users. It has a single hidden layer neural network. And again, the black curve is the accuracy versus iteration of our proposed scheme with two-dimensional lattices. The blue curve is the performance of our proposed scheme with one-dimensional lattices. The green curve is QSGD, which is pretty much state of the art. And as we can see, we converge to improved performance when operating at quantization rate of 4 bits per sample. And as we can see, our approach allows us not only to obtain improved distortion when recovering the weights, it also allows us to obtain improved convergence of federated learning. So In this talk, I presented a scheme based on universal quantization for federated learning, which combines tools from quantization theory with distributed learning, and it exploits a specific characteristic of a federated learning setup, which include a source of common randomness and the statistical heterogeneity of the data, which denies us from prior knowledge of the underlying statistical distribution. Now, we saw that as a result of this scheme, the distortion is mitigated by not only just by averaging, but also by decaying step size. Namely, as the iteration progressed, we're actually getting more and more accurate results. And it obviously boosts convergence, as we proved analytically and showed numerically. And we can see notable gains over previously proposed federated learning schemes. Now, that's it. I don't have a link to the paper on arXiv here, but I'm pretty sure that by the time this video will be presented, I will have it ready on arXiv, and I welcome you guys to come and check our paper out on arXiv. And I want to thank you for coming to my talk, for listening. And please feel free to ask any questions and be in touch. Thank you very much.